Welcome Algebra 2 students to some late night video action with the properties of exponents and roots and radical expressions. So in the purple book you have at home, this is chapter 7. In the online textbook, this is chapter 6. Alright, let's jump right in with some review of the properties of exponents from Algebra 1. 7 basic properties of exponents. So let's start here with the product of two powers. You can keep the base and add the exponents. That's the product of powers rule. As long as you have that same base, you keep that base, add those exponents together. Power of a quotient. You can raise each of the parts of the quotient, so the numerator and denominator, to that power. Any value to the 0 power is always equal to 1, not including 0. 0 to the 0 is undefined, but a to the 0 power is equal to 1. If you don't remember why that is, remind me in class and we'll go over it. It's just a very simple and quick look at a pattern. Okay, the quotient of two powers that have the same base, keep the base, subtract the exponent. So it's like the product rule becomes a product of two powers, the sum of the exponents, the quotient of two powers, the difference of the exponents. Any value to the negative n, so a to the negative n, is 1 over a to the positive n. It's a reciprocal maker or an inverse maker, multiplicative that is. So a negative exponent, you can always take it, put 1 over, and put that base with a positive exponent in the denominator. The power of a product, we raise both of the factors to that product, or all of the factors to that product if there were more than 2. And the power of a power, we multiply our exponents here. So these are the basic properties of exponents, and we're going to go ahead and apply them in a couple of examples. And there's a whole page of this in your textbook that has some good practice that I can give you the answers for if you feel like you need extra practice. But let's try these 3. So the first one we have is a product. So we're multiplying these two monomials together. Monomial's one term, mono. Let's multiply the coefficients. So we'll start with 5 times negative 3 is negative 15. And now we have a to the third times a to the negative 4. Now I could have rewritten this as negative 3 over a to the 4th. I could have rewritten it that way. But since I have two powers that have the same base, I can just keep that base. So negative 15 is the coefficient. Keep that base and subtract those exponents. 3 minus negative 4, 3 minus negative 4, make sure there's like minus signs, is 7. So this is negative 15, a to the 7th power. All right, next one. So this is a power of a product, or a power of a monomial. So we're going to start with raising the negative 4 to the 2nd power. So negative 4 squared is going to be 16. And then we have the x to the negative 3 to the 2nd power. That's going to be x to the negative 6, and then we have y to the 5th, also squared. Okay, so this is going to be 16 is my coefficient. Positive, remember, you square a negative, you get a positive. X to the negative 6, we'll come back to that. We can't leave it that way. And y to the 10th, power of a power, we multiply these exponents here. Now we can't leave this in a product, so we're going to drop it down. We're going to keep the 16y to the 10th. That's your numerator. You really do have a denominator here. It's an invisible 1 underneath right there. So instead we're just going to drop that x to the 6th down in the denominator. And we're going to use the stipulation x can't be 0. All right. Last one, a quotient of two powers. We don't have anything to simplify with the coefficients. Still going to be a 4 up there. I like to do this one by canceling out the common, what's in common in the numerator and denominator, like 1a, so one of these 5a, so that becomes a to the 4th in the denominator. This 1b takes out one of these, makes that b to the 5th. And c to the 3rd and c to the 3rd would actually cancel out, so we've got a bunch of space we don't actually need right there on our fraction bar. And again, we should give that stipulation a can't be 0. All right, so we'll do a little more practice with that in class, but these are review skills, so if you're struggling with this, find that extra page in the textbook and practice some more. Okay, roots and radical expressions. If a to the n power is equal to b, with a and b real numbers, and n a positive integer, then a is the nth root of b, or a is the nth root of b. Something like that, which is, you can see actually later down the page here. Now, if n is an odd power, what you see here, if n is odd, there is one real nth root of b, and it's denoted in radical form as you would see it right here, just like that. So if it's odd, there is one real nth root of b. So that would be for cube roots and so on, odd powers, or odd indices. We'll get to the vocabulary in just a second. If b is positive, if n is even and b is a positive, there are two real nth roots. And now this goes to our plus or minus rule. Positive root is the principal root or principal nth root, and its symbol is the nth root of b. The negative root is the opposite. And so all that says, all that mumbo jumbo says, is like saying the square root of 16, because the invisible 2 that's sitting here is even, is actually plus or minus 4, and not just positive 4 and not just negative 4. And then if b is negative, there are no, so this is if the square root, say, of 16, but it was a negative 16, no real root exists. So that's all that mumbo jumbo is saying. And the only nth root of 0 is 0. So 0 does have a root, no matter what the index. And so to get back to that vocabulary I was just talking about, that's what you have here. So this inside is the, inside the radical sign is the radicand, the value, the number there. The radical sign is the funky check marks division box thingy. And then this number is called the index. And that's the number, the value of the root that we're actually finding. So the cube root, for example, of 27 is saying what to the third power is 27. Well, I know I picked an easy one. So what to the third power is 27? Well, that would be 3. Okay, and remember that if, just like we saw on the previous page, if I had a negative, that would be negative 3. But if I was talking about the square root of 25, we can say that's plus or minus 5, but the square root of negative 25 is a non-real number. Okay, so that kind of lays it all out for you with the vocabulary. So let's take a look at some examples. Okay, so what is each real number root? Go ahead and give them a try, and then I'll run through them for you. Okay, hope you paused it. If you didn't pause it now. All right, we just did this one. Cube root of negative 27, negative 3. Fourth root of negative 81. Well, 4 is even, so that means that this root is not a real number because we have that even root, so we can't have a negative. All right, so in here we have negative 7 squared, the square root of that. Well, that's going to have a principal root of positive 7, and the other one, negative 7, the other square root, negative 7. And this one is, again, not a real number because you can't have an even root of a negative. So now we look at what you do when you have a larger expression under that radical sign. So this one is actually pretty straightforward. The square root of 81, we know that, that's 9. And the square root of x to the 4th, my shortcut for this is to put the exponent over the index and divide. So in this case you have 2. So that's 9x squared. Fabulous. Now, notice though that with these problems, we can't just assume that the x values are all going to be positive or negative, that they that would actually be plugged into these expressions. So we do have to actually make some rules, kind of like what we were doing on the previous page where you couldn't have a denominator equal 0. Now in this case, x could be a negative or a positive because in the end, when you square the x in the answer, it takes away a negative. So there's no stipulation, there's no kind of restriction we have to put on this answer. But we will have one before the end of this assignment here. All right, next one. All right, so again, if we had a coefficient, we would find the cube root, but we're not going to do that. We're going to do a to the 12th, so we're going to write it as the base, and then as I said, exponent over index. You can divide them. Because it's asking what times itself 3 times gives you a to the 12th. Well, how many times does 3 go into 12? Goes in 4 times. All right, and the same thing, base is b, so 15 over 3, and that goes in 5 times. Okay, it was an odd root, so we don't need to worry about any restrictions on any variables. You can have a positive or negative in for any of those variables. All right, how about this one? Again, no coefficient, so x to the 12 over 4, so x cubed, and y to the 16 over 4, so y to the 4th. Now, this is a little bit of a tricky subject here, but what's going to happen with this one is we had an even root here, an even index, even root. So, if x had been a negative value that was plugged in, when you actually evaluate the expression, you couldn't do that. You couldn't have a negative because a negative x, right here, a negative x to the 3rd power would be negative. So how you fix that, the restriction you put on this is you put absolute value bars around the x cubed. And so you use the absolute value bars when you have an even root that has an even exponent that ends up with an odd result when you simplify it. The odd exponent in the result. That's when you need the absolute value bars. Okay, trudging onward. Okay, we're making good time, so I'm going to keep on trucking. All right, so properties of radical expressions now. Okay, so if you have the nth root of a and the nth root of b, and you want to multiply them, you can go ahead and multiply those radicands together and combining the two radicals under that same nth root. Notice the index must be the same in order to do that. You can do the same thing with division. You can combine the two parts of the fraction. You can go opposite directions on both of these. So in other words, if you have a product, you can split it apart. If you have a quotient, you can split it apart, or you can put it back together and vice versa. Use the distributive property to add or subtract like radicals. This is a little bit different, but here all we're really saying right here is if I have so many nth root of x's minus another number of nth root of x's, it's this part matching that's important. We can go ahead and just subtract the coefficients and then keep that nth root of x on it. So that's all this is saying, and if you have the sum, you can do the same thing. Let's practice with it because I think it'll get easier to see if we're actually doing the math. Okay, some practice with the skills that we just, or the properties that we just looked at. So, number 1, product of 4th root of 64 and the 4th root of 32. So the 4th root of 64, I'm going to write both of these values inside the radicals. I'm going to write them as powers of 2. So this is a 2 to the 6th, 4th root of 2 to the 6th times the 4th root of 2 to the 5th. And I can multiply them and make it the 4th root of 2 to the 11th power. And because there are 2 powers of 4 there, that's 2 to the 4th, no, don't forget your index, 2 to the 4th, 2 to the 4th, so that's 8, and 2 to the 3rd left over in there, I can go ahead and actually take out those 2 to the 4th. So the 4th root of 2 to the 4th is 2. And another 4th root of 2 to the 4th is 2. And then the 4th root of 2 to the 3rd power left inside, or 4 times the 4th root of 8. So there's that first one. Whew, that was exhausting. Okay, so number 2, the 4th root of 162x to the 6th power. So we need to figure out what there is in that 162. Very quickly, I'm seeing 162 is 2 times 81, and 81 is a perfect fourth, a 4th power. That's 3 to the 4th power. 3 to the 4th. All right, so 162 is 2 times 3 to the 4th. And then I'm going to write x to the 6th as x to the 4th times x squared. Let's switch colors so we can see what we're doing here. I can take these two out. So the 4th root of 3 to the 4th is 3. The 4th root of x to the 4th is x, except I need absolute value bars because it is an odd power coming out of an even root, and then 2x squared left inside the radical sign. Awesome. Moving on. Number 3. All right, so those are pretty big numbers right there, so I'm going to put it all the way back together, but I'm going to break up the 54 and the 72, and I do know that 54 and 72 are both multiples, thank you, multiples of 18. So 54 is 3 times 18, and I'm going to go ahead and rearrange the whole thing. So I'm putting the whole thing back together, or not back together, but together, because that's one of my rules. That's my product of radicals rule from the previous slide. So 3 times 18 for 54, and 72 is 2 times 18. No, it's not. It's 4 times 18. Let's try that again. There we go. And then I'm going to multiply x to the 4th times x is x to the 5th. And y cubed times y to the 6th is y to the 9th. Okay, so this is just a plain old square root. So what can I take the square root of? Well, I can't take the square root of 3, so it's going to stay in the radical. I've got a double factor of 18. So I can take the square root of 18 times 18. That's going to be 18. I can take the square root of 4. That's going to be 2, and I'm going to multiply those outside. X to the 5th, well, there's x to the 4th there, and I can take the square root of x to the 4th. So x to the 5th is x to the 4th times x. I can take the square root of x to the 4th, so x squared can come out, but that x has to stay inside. And y to the 9th I can break up. That'll be y to the 8th times y. And I can take the square root of y to the 8th, so that's y to the 4th, and that y has to stay inside the radical sign. So inside the radical sign I have 3xy left. Multiplying that outside front portion there, that factor, that coefficient, 18 times 2, 36. 36, x to the 2nd, y to the 4th. I'm almost out of space, 3xy. Oof, almost didn't make it. Okay, last slide, 3 more problems. I'm sorry, I know this is getting lengthy, but this won't take too long. Number 1. Okay, number 1. So we have square root of 180 minus the square root of 80 plus the square root of 45. Each of those has a perfect square factor. So 180, for example, has a perfect square factor of 36. So 180 is 36 times 5 minus 80 has a perfect square factor of 16. 16, again, times 5, I think. Yeah, that's right. And perfect square factor in 45 will be 9 times 5. And notice they all also have that factor 5 in common. Well, isn't that interesting? And that is kind of the point of what they were giving us here. I can take the square root of 36, that's 6, so 6 root 5, minus I can take the square root of 16, that's 4, so 4 root 5, plus I can take the square root of 9, that's 3, so 3 root 5. And now we're going to treat them like they were variables, kind of like we saw in that previous slide. So 6 minus 4 plus 3, root 5s. 6 minus 4 is 2, plus 3 is 5, 5 root 5. As for these two little expressions here, 2 and 3, you're going to FOIL. So very quickly, foiling out that first one, we're going to start with first is 20. Outer is minus 24 root 3. I like to line it up vertically, so I'm going to write my inner minus 5 root 3 underneath that. And then minus root 3 times minus 6 root 3 is minus 6 times root 3 is 3. So root 3 times root 3 is 3 times 6. That's going to be an 18, except it's going to be a plus 18. So 20 and 18, that's 38. So 38 minus 29 root 3. Last one. This one's actually pretty awesome because these are, what did we learn about with the complex numbers? These are conjugates. So conjugates, when you multiply them, oh no, sorry, editing jump, conjugates. When you multiply them, that's that difference of squares pattern. So 8 times 8, 64. The outer and the inner will cancel. Radical 20 times radical 20 is 20. So 64 minus 20, when you multiply those, you actually get 44. Weird. All right, a little extra long, but thanks for plugging away with it. See you guys in class.